And on page 43, at the top, we were learning about the action potential. The action potential is a short-lasting reversal in the electrical polarity of an excitable cell that is then conducted along its length. Every cell has a membrane potential of an electrical voltage. Every cell. But only excitable cells, meaning nerve cells and muscle cells, can exhibit a reversal in the electrical polarity, where it goes from being the normal negative on the inside to positive on the inside, and then returns back to being negative. And this acts like a signal that can be conducted along these long nerve fibers or muscle fibers, like a signal. So how does this work? Well, first of all, again, we remind you that there's these ion channels. We know that normally the only ion channels that are normally open in all cells, including nerve and muscle cells, are potassium ion channels. But in the case of a nerve cell or muscle cell, excitable cells, if they're stimulated, the sodium ion channels momentarily, briefly open up. And when that sodium starts to flow into the cell, that's going to change the electrical polarity in the cell. So the way I wrote this here, depolarization, a term we've used before, simply refers to the membrane potential becoming less polarized, really less negatively polarized than normal. And it results after an excitable cell, a nerve cell or muscle cell, is stimulated chemically, mechanically, or electrically. What normally stimulates nerve cells and muscle cells naturally in our body is mostly chemicals called neurotransmitters. Here I wrote somewhat cryptically that when you stimulate an excitable cell, a nerve cell or muscle cell, it causes a transient. What's transient mean? Good, short lasting. It's written at the top of the page, right here. Short lasting. So it causes a short lasting increase in permeability to sodium. This little P with the sub Na is standard. It's a lot of books write it that way. All that means is that the sodium channel's open, so that the membrane is more permeable to sodium. The sodiums go into the cell, and why are the sodiums rushing in? There's both a concentration gradient and an electrical gradient pushing them in. Now, we're skipping page 44. We're skipping page 44. And the top of 45, I'm not going to get into the roles of calcium. But how does the cell repolarize? So as we learned last time, we might have thought, I certainly thought when I was learning this, that if the sodiums go into the cell, and that reverses the electrical polarity, then the sodiums must just go out of the cell and it repolarizes back. That's not what happens. The sodiums rush in, and then they're trapped on the inside because the sodium channels have closed. But what happens is additional potassium ion channels open up. And these additional potassium channels that open up are known as voltage-gated potassium ion channels. We're going to see that written in just a moment. There are ligand-gated and voltage-gated ion channels. This is covered in videos. It's covered in chapter 12 of your book. Your book actually lists 4 categories of ion channels. I'm only asking you to know 2 of the 4. All right, so voltage-gated and ligand-gated. Anyhow, these voltage-gated potassium channels open up, and the potassiums now rush out of the cell. And what's causing the potassiums to rush out is both a concentration gradient and an electrical gradient pushing out. That's different than the normal resting membrane potential where the electrical gradient is in the opposite direction of the concentration gradient. As the potassiums go out of the cell repolarizes. So in a nutshell, here's how I summarized it on the bottom right. Sodiums going in cause a depolarization and a reversal in electrical polarity. Potassiums going out cause a repolarization, a return back to being negative on the inside, positive on the outside. But of course, that means we've got the wrong ions on the inside and on the outside. Too much sodium on the inside, too much potassium on the outside. So on the next page, 46, we said that it's then the role of the sodium-potassium ATP pump to kick the sodiums back out of the cell and in exchange bring the potassiums back in. But this doesn't repolarize the cell. So the cell repolarized once the potassiums went out. Now, the way this is always depicted is in this graph that we've looked at last time. This is simply a graph of changes in voltage in this excitable cell. Here's this, we'll say this is a nerve cell, and we put a microelectrode into that cell, and we're monitoring its voltage. And the voltage starts out, the voltage in this cell starts out at about minus 70 millivolts. Remember, there's kind of a range of these volt-negative polarities. Some cells are 60 millivolts negative on the inside, some 70, some 90, so it's just approximately in that range. So it's starting out at minus 70. Now you'll notice right here it says we stimulate the cell. So I drew a kind of dashed line up, we stimulate it, and what does that do? It opens up sodium ion channels. That's what this is showing, an increase in relative membrane permeability to sodium. As the sodiums start to flow into the cell, that's going to make the inside of the cell become less negative. So it's going minus 70, minus 60, minus 40, minus 20, 0, plus 20, plus 30. Most nerve excitable cells usually go from being negative 70 or 90 millivolts to about plus 30. There is a reason why it goes to plus 30, because you might have said, well, why doesn't it, if it starts at minus 70, why doesn't it go to plus 70? There is a reason. Your books talk about it. I'm not. I won't ask you to know. Okay? But there is a reason. But anyhow, the sodiums go in. And then, that's called depolarization. And then this reversal in electrical polarity causes an increase, opening up of potassium ion channels, and the potassiums flow out. Here's where it shows the membrane permeability of potassium increases. And as the potassiums go out of the cell, it repolarizes. Commonly, it overshoots, and it actually becomes briefly more negative than it even started out. That's called an after hyperpolarization. Hyperpolarize means to become more negative than normal. And why does that happen? Well, just think about it. If 100 sodiums went into the cell, but 125 potassiums went out, then more positive charges would have gone out than went in. And it would be hyperpolarized, it would be more negative. That's what I wrote right here. Right? So after hyperpolarization results if more potassiums go out of the cell than the number of sodiums that went in. But eventually it kind of reorganizes itself and it returns back to being the normal electrical polarity. Now, we also showed you the same thing on page 46A. So let's go through that really quickly again. So here it is. These are the steps of the action potential. The cell starts out negative on the inside. These are the ionic balances. All right? Then it shows we're going to stimulate the cell. All right? What normally stimulates an excitable cell is a chemical, a neurotransmitter, that causes an opening up of a sodium ion channel. Now, these are known actually as ligand-gated sodium ion channels because what's opening up the sodium channels is in response to a ligand, a neurotransmitter. All right, and the sodiums rush in because of both the concentration and electrical gradient. And as the sodiums flow into the cell, the inside of the cell becomes less and less negative, it depolarizes, and then it even starts to become positive. It reverses electrical polarity. So it looks like what we see on the top of page 46b. So now you'll notice that our electrode inside the cell now reads plus 30 millivolts. The inside of the cell is now positive. It has reversed electrical polarity. But it's not that the sodiums now go out, it's actually voltage-gated potassium channels open, and more potassiums rush out of the cell. Now, why are the potassiums rushing out? Now, not only is there a concentration gradient pushing potassiums out, but there's also an electrical gradient, because the inside of the cell is positive. Normally, in the resting state, the inside of the cell is negative. So both forces are pushing potassiums out. On page 46C, as the potassiums go out, the inside of the cell repolarizes back to being negative. So now, our microelectrode is telling us the inside of the cell is negative and the outside is positive. The only problem is we got too many sodiums now on the inside and too many potassiums on the outside. And that's the role of the sodium-potassium pump, is to kick the sodiums out and bring the potassiums back in. All right, and so finally, after that, the cell is totally back to normal after the pump. And incidentally, how long does it take this pump to kick those sodiums back out and potassiums in? What does it take? About 20 minutes, an hour and a half? About 10 milliseconds. 10 milliseconds. So it's measured in thousandths of a second. Let's go back to page 46. The electrical recovery period, we said that after you stimulate an excitable cell like a nerve cell, you got to wait a certain amount of time before it will generate another action potential. It needs to recover. And typically nerve cells need about 10 milliseconds to recover. So we can actually say that if you know that the nerve cell needs 10 milliseconds between one action potential and the next, we could calculate the maximum number of action potentials it could generate in a second, which is about 100 action potentials per second or per minute or whatever. And so every nerve cell has a maximum frequency of action potentials, because no matter how loud the sound is, at a certain point, those sensory neurons in your ear are firing off the impulses as fast as they can. So let's take a look at page 188. On page 188, here's what we said last time, page 188. We were talking about the electrical recovery period. The electrical recovery period, or refractory period, in heart cells. Now, heart cells have an electrical recovery period not of 10 milliseconds, but 0.3 of a second. How many milliseconds is that? 0.3 of a second is, how many milliseconds? 300 milliseconds. So this is much longer recovery time than in nerve cells, which is just 10 milliseconds. Now, we're going to learn when we get to this page formally that that's because the action potential in a heart cell is very long. You see, an action potential in a nerve cell looks like this. It's about 1 millisecond, but in a heart cell it depolarizes and it takes a long time before it repolarizes. When we get to the heart cells, that's because we're going to explain not only do sodiums flow in, depolarizing it, but then calcium ions flow in, keeping it depolarized. Finally, potassiums flow out. So this is why, when we get to the heart, we're going to learn that there are drugs that work on the heart cells, but don't affect nerve cells, known as calcium ion channel blockers. At the bottom of the page, we wanted you to calculate the theoretical maximal heart rate. We all know that when we start exercising, we start running, our heart rate speeds up. But there's got to be a limit. There's got to be some sort of limit. And actually what limits how fast your heart can beat is the maximum number of action potentials your heart cells can generate and transmit. So we said that heart cells can generate, they need 0.3 of a second between each action potential. They need at least that. And for every time there's an action potential, you get 1 beat of the heart. So we asked you to calculate the maximal heart rate of beats per minute. So hopefully you tried it. What did you get? What's the theoretical maximal heart rate? 200 beats a minute. The math is always very simple. Let's see how it works. All right? So, look, think about this. We know that these heart cells can generate 1 action potential every 0.3 of a second. I'm setting it up just like we did on the bottom of page 46, where nerve cells can generate 1 action potential every 10 milliseconds. If we can figure out the maximum number of action potentials heart cells can generate in a minute, then that's the maximum number of times it can beat in a minute. Because every time there's an action potential, we get a beat. So let's just go from seconds to minutes. There's 60 seconds in a minute. The second units cancel out, so it becomes 1 times 60 is 60. The units on top are action potentials. On the bottom, 3/10 times 1 is 3/10. The units on the bottom are minutes. So can we divide 3/10 into 60? Yes. So what's 3/10 into 60? 200 action potentials per minute. So heart cells can fire up a maximum of 200 action potentials per minute. All right? Remember, nerve cells can fire up a maximum of 100 action potentials per second! Per second. So if the heart cells can fire off up to 200 action potentials per minute, that means they can beat, the heart can beat up to 200 times a minute. Because every time there's an electrical current moving through your heart, it causes a contraction or beat of the heart. Now, even if you looked at this stuff, even if you're scratching your head going, I have no idea what the hell he wants me to do. If only you would have looked on the next page, page 189. Look at page 189, and what is the graph on the top left on 189? What does it say? Maximal attainable heart rate. That's what we wanted you to calculate. And according to the graph, what does it show as the maximal attainable heart rate? 200 beats a minute. So, and that's because of the electrical recovery period between each action potential. Now, another thing you'll notice on this graph, it indicates heart rate in beats per minute on the y-axis, and what's on the x-axis is how old you are. So what do you notice happens to your maximal attainable heart rate as you get older?
It goes down.
It goes down. You can't get it up like you used to. All right? Can't get it up like you used to. So you'll notice that as you get older, now most of you are about, in the 25 years of age, so your maximal attainable heart rate is 200 beats a minute. Now what's this target zone? You remember how we learned how to make your heart stronger, bigger and stronger to improve your endurance?
Exercise.
You have to, now we know to make your arm muscles stronger, you lift weights. To make your heart stronger, you have to speed up the heart rate. But how fast do you have to speed up your heart rate? You have to get it somewhere between 70 to 85% of its theoretical maximum to make your heart become bigger and stronger. That's called the target zone for a cardio workout. That's called a cardio workout, right? A heart strength, exercise that strengthens your heart. Now, let's say it's about 80%. So you want to get your heart rate up to 80% of its theoretical maximum. If your theoretical maximum is 200, what's 80%, 0.8 of 200?
160.
160. So your target is about 160 beats a minute. Now, for the age that I am, all right, I would stroke out if I tried to get my heart rate up to 160 beats a minute. My heart rate cannot go 160 beats a minute. That's why if you've used a machine, like a treadmill, they often ask you to punch in your age. Does anybody know what I'm talking about? They'll ask you to punch in your age to give you a workout because they're not going to be as demanding if you're 75 years old. I'm not quite 75. But if you're 75 versus if you're 25. But you've got to get 80% of whatever your theoretical maximum is. There's kind of a rule of thumb to simplify this chart. If you take the number 220 and subtract your age, that will give you your approximate theoretical maximum. So if you're 20 years old, your theoretical maximum is 200.
It's like the maximum heart rate is 200, but I know there is like something called fibrillate that you go
Yes.
700.
When the heart goes into fibrillation, it's no longer beating. It's just shaking.
Oh.
It's just quivering. And it's quivering at 300 or 400 times a minute, but just quivering, it's not beating. Let's go back to page 47. And on page 47, so we want to talk about coding for stimulus intensity on page 47. So this picture is showing where we're stimulating a nerve cell. And we've already learned that when we stimulate a nerve cell, sodium channels open. And now, the stronger the stimulus, the more sodium channels open. And the more sodium channels that open, the more sodiums flow in and start to change the electrical polarity of the cell. Now, let's look at this graph. Now, we can of course take a microelectrode and put it in a nerve cell and monitor the voltage in this cell. So on this graph, on this graph, what it's showing is increasing stimulus. Now, maybe we're giving increasing electrical shocks to a nerve cell. Maybe we're increasing the volume of sound to a sensory neuron in your ear. Maybe we're increasing the amount of neurotransmitter being released onto this cell. It doesn't matter. We're increasing the size of the stimulus. Notice that with a tiny stimulus, the voltage changes a little bit. That means with a tiny stimulus, a few sodium channels open, and a small number of sodiums enter the cell, and it depolarizes a little bit, like from -70 to -65. All right, a little bit. And then it repolarizes back. Is that an action potential? No. The definition of an action potential is a complete reversal in the electrical polarity of the cell, where it actually becomes positive on the inside. This is still negative on the inside. This is called a subthreshold stimulus, and these are called subthreshold voltage changes or local responses. So here's what I wrote. The effect of a subthreshold stimulus is that a subthreshold stimulus causes a local increase in permeability to sodium. That means sodium channels open, and we get a little local depolarization. It just depolarizes right here a little bit, from -70 to -65. And then it recovers. Then it just repolarizes back. Let's give a stronger stimulus. Notice that a stronger stimulus will open up more sodium channels, more sodiums will enter, and it depolarizes more. Is that an action potential? No, it's still not an action potential. Let's give it a stronger stimulus. Give it a stronger stimulus, even more sodium channels open, more sodiums flow in, it depolarizes even more, and it repolarizes back. Is that an action potential? No. But eventually, we give a stimulus that is strong enough where we get one action potential. It appears that we have to depolarize a cell to what's called a threshold level in order to generate the action potential. Now, what's a threshold? What does that mean? So let me give you a couple of examples of this concept of threshold. First off, I drew this amazing picture at the bottom. Imagine a guy is trying to push a boulder over a cliff. Now, if he just pushes a little bit, the boulder may move a little bit towards the edge, and then it just rolls right back. Did the boulder go over the cliff? No. But eventually, if he pushes enough, the boulder will reach this threshold, or edge of the cliff, and once it reaches that edge, there's no stopping it. So that's the concept of a threshold. You've got to reach, you've got to push the boulder, you've got to depolarize the cell to some critical level in order to get the action potential. Let me give you another example, and I can't remember if I did this last class meeting or not. Right now, you can all hear my voice. Let me lower, did I do this last time or not? No. Okay, I'm going to lower my voice. I'm going to turn off the mic. All right, you can all hear me right now, right? I'm going to speak a little softer. Okay, I'm lowering my voice. You can still all hear me. I'm going to lower my voice a little bit more. You still hear me, right? Listen, can you hear me in the back? I'm going to lower my voice. Okay, now I've lowered my voice. It's getting a little bit difficult for the people in the back row to hear me. I'm going to lower my voice more. Now, Elon can still hear my voice, right? You can hear my voice. People in the back can no longer hear my voice. I'm going to lower my voice. Now, you can still hear me. You can still hear me. In other words, what happened? What happened? Why couldn't you hear me? When the volume of my voice dropped below the threshold level, your sensory neurons in your ears were no longer firing off an action potential and sending it to your brain. It doesn't mean there's no sound in the room. It's just that the sound isn't loud enough to activate the sensory neurons in your ear. This is the basis of audiology, or hearing tests. Has anybody ever had your hearing tested? That's where they'll play sounds, and they lower the volume to the point where you say, I can't hear it. And they know what's normal. They know that normal people of a certain age should be able to hear a certain volume, but not another volume. So if they do a hearing test, and they're playing a sound that a normal person would be able to hear, and you can't, then you have impaired hearing. Does everybody follow that? This is true for everything. There are thresholds for everything in the nervous system. It's true not only for sound, it's true for light. If we dim the light more and more and more in this room, eventually this room would look dark, totally dark. That doesn't mean there's no light here. It's just that it's dropped below the threshold to activate the photoreceptors in your eyes. The same is true for touch. Now, if you touch your skin, you can feel it. Have you ever been like at the park, at a picnic at the park, and you only noticed an ant crawling on your leg? And you had to see the ant crawling on your leg because you did not feel the ant crawling on your leg. Because the touch of the ant was too light to activate the touch receptors on your skin. So everything has a threshold. So that's what we're talking about here. So you've got to use a certain size, certain volume of sound, a certain amount of touch, a certain brightness of light, a certain amount of neurotransmitter to depolarize, to allow enough sodiums to enter, to depolarize the cell to the threshold level. And once it depolarizes approximately to minus 50 millivolts, that's the usual threshold level, then there's no stopping it. And action potential fires off and is conducted or sent along that nerve cell. It's like reaching the threshold of the cliff. Once you reach that threshold, let's see it. On the next page, the boulder goes over. So we wrote on the top of page 48. On the top of page 48. So a threshold stimulus is a stimulus that is strong enough to increase the permeability to sodium, to make enough sodium channels open so that it reaches a critical level of depolarization called the threshold potential, and we end up with a complete reversal in the electrical polarity of the cell. Okay, that's a threshold stimulus and and an action potential. Now, going back to the previous page, 47. So here's this graph. Here's the threshold stimulus. It causes an action potential. Anything less than that did not cause an action potential, meaning no signal was sent to your brain. Doesn't mean that this nerve cell wasn't responding, but it didn't send a signal. An action potential is a signal. Now, what if you used a suprathreshold stimulus? You'd say, what's that? A stimulus greater than threshold.
Doesn't matter.
All right? Well, let's see. When they used the suprathreshold stimulus, was there any difference in response than using a threshold stimulus?
No.
Yes. In response to a suprathreshold, it caused 1, 2, 3 action potentials in a row. So in other words, any sound greater than threshold, as I increase the volume of my sound, it's sending a higher frequency of action potentials. Didn't we cover this back on page 46? You'd say, what do you mean? On page 46, didn't we talk about playing a sound to a moth? Wasn't this showing the increasing frequency of action potentials as we increase the volume above threshold? So once we go above threshold, right, threshold just causes 1 action potential, increasing suprathreshold stimuli cause a higher and higher frequency of action potentials until it reaches its theoretical maximum. This is the way our nervous system is transmitting signals or information. So we wrote on page 48, so what's the effect of a suprathreshold stimulus? It triggers more than 1 action potential in a row. The action potential looks the same. It's the frequency of action potentials that increases. Okay. It's not like the action potential becomes taller. It doesn't become bigger. You just get more of them. This is the way our nervous system is communicating information. All right, now that we know about this, how our nervous system works in response to subthreshold, threshold, and suprathreshold stimuli, let's talk about, on page 48, the conduction of the action potential along the nerve fiber or muscle fiber. Once an action potential is generated, it's going to be sent along the nerve cell or muscle cell. Now remember, nerve cells and muscle cells are unusual cells. They're not simple round cells, they're really long cells. That's why they're called fibers. So the only cells we call fibers are nerve cells, nerve fibers, and muscle cells, muscle fibers. And so this action potential is conducted. Now we know that there are unmyelinated and myelinated nerve cells. All muscle cells are unmyelinated. There's no such thing as a myelinated muscle cell. How is an action potential conducted in an unmyelinated nerve cell? So what I wrote here, and this will sound like a physiology book, as the nerve fiber depolarizes, it triggers an increased permeability to sodium in the next adjacent region, causing that region to depolarize. You'd say, yeah, what does that mean? Let's look on page 49. Here's page 49. So this is a picture of an unmyelinated neuron. It's in the resting state. You'd say, what does that mean? What it means is it's negative everywhere on the inside of the cell. It's negative on the inside, positive on the outside. Now, it's in the resting state. Let's stimulate it. We're going to give it a threshold stimulus generating one action potential. If we use the suprathreshold, we get more than one action potential. Now, let's look in the middle picture. In the middle picture, right here in the circled area, is where the action potential is at this moment. This is where the sodiums are flowing in. And it's reversing electrical polarity right in this circled area. Everywhere else, it's still negative on the inside. It's still in the resting state. Only in this circled area has the electrical polarity reversed. That's where it's reversed electrical polarity. Now, I wrote that the reversal in electrical polarity, right here, where it's reversed electrical polarity, that causes voltage-gated sodium ion channels to open in the next adjacent region. There are voltage-gated sodium channels that open up when the voltage of the nerve cell changes. So when this voltage in the cell reverses electrical polarity, it causes, in this area right here, voltage-gated sodium channels to open. So the next place, here's where sodium channels are open at this moment. The next place where the voltage-gated sodium channels are going to open is right here. That's what it shows right here. Here's where the sodium channels have now opened up, and the sodiums are flowing in down their concentration electrical gradient. Meanwhile, what's happening here, where it had been reversed in polarity? It's repolarizing back. The potassiums are going out. This is where the potassiums are going out, repolarizing it. Now, if we had a fourth picture, where's the next place the voltage-gated sodium channels are going to open? Right here. All right, so in the next picture, the circled area would be here. Sodiums would be flowing in here, reversing the polarity. And what would be happening here? It would be repolarizing as potassiums go out. So literally, this phenomenon of sodiums going in and then potassiums going out is just repeated along the entire length of the nerve fiber. So this, quote, action potential of sodiums going in followed by potassiums going out is simply replicated over and over along the length of the nerve fiber. The term they use is it's propagated. Now, an analogy that I'd like to use, and I can't remember if I gave this analogy last time or not. You've all dropped a rock into a lake. And when you drop a rock into a lake, it causes a wave or a ripple, right? Now, if you drop a grain of sand into the lake, you don't get anything, right? That's like a subthreshold stimulus. If you drop the smallest little rock that would cause one ripple, that would be a threshold stimulus, and it causes one little wave or ripple. If you use a larger rock, you don't just get one wave or ripple, you might get a whole series of them. Does everybody follow what I'm saying? And that little ripple or wave is just moving along the surface of the lake, just like an action potential is moving along a nerve fiber. Just like that little wave. You dropped a rock into the water, and this wave starts to move. all right, away from where you first dropped the rock in. You stimulated the nerve cell, we get this wave called an action potential that's moving along the nerve fiber. So in fact, I wrote this on the previous page, on the bottom of page 48. That's exactly what I wrote. I wrote, visualize dropping a rock into a lake that causes a ripple to move across the surface of the water. The ripple is a rising and then a falling of the water. That's what that ripple is. It's a wave. The water level goes up and then it goes down. And this reminds us of the depolarization as sodiums go in and the repolarization as the potassiums go out, which it looks like a wave. It looks like a ripple. And that's how it's moving. All right, now, let's look on page 50. Incidentally, on page 50, at the top, it shows you what it would look like if here's a nerve fiber, if there's more than one action potential moving along that nerve fiber at the same time. Remember, if you use a suprathreshold stimulus, you don't just get one action potential, you get more than one. So here's maybe one, and here's another one, and they're both moving along. It's like two waves or two ripples in response to dropping a rock into a lake. Now, what about in a myelinated nerve fiber? In a myelinated nerve fiber, we wrote the depolarized node of Ranvier triggers an increased membrane permeability to sodium and thus depolarization in the adjacent node of Ranvier. This is known as saltatory conduction. So you'd say, what? What? Okay, so let's show you a picture of that. I'll come back to that page. Let's look at page 52A. So this is showing a myelinated neuron. You'll recall that in a myelinated neuron, there are these myelinating cells wrapped around the nerve fiber. It's like insulation, like a plastic coating, but it's a living cell. But there are little gaps between those myelinating cells. What are those gaps called? Nodes of Ranvier. Now, I'll also remind you that what we call the myelinating cells is that if the myelinating cells are wrapped around an inner neuron, they're called oligodendrocytes or oligodendroglia. But if they're wrapped around a sensory neuron or motor neuron, they're called Schwann cells. The only places where sodiums can go into the nerve fiber are at the nodes of Ranvier. The sodiums cannot enter the nerve fiber where it's surrounded by this myelinating cell. So, right here, it's showing sodiums are going in, and this is the area where it's reversing electrical polarity. This is the area, as the sodiums go in, it's going to reverse electrical polarity here. Everywhere else, it's still negative on the inside. Now, the sodiums go in. Where's the next possible place the sodiums can now enter this nerve fiber? Here. So look at this picture. Can everybody see sodiums are now entering at this node of Ranvier? Meanwhile, what's happening here? The potassiums are going out. Now, where's the next place that the sodiums can go in? Right here. So the next place the sodiums go in is here, and what would be happening here? The potassiums are going out. So what we see in this case is it's very similar to unmyelinated neurons. Sodiums go in and then potassiums go out, but it's occurring only at the nodes of Ranvier. So what happens in this case is called saltatory conduction. And you'd say, what's that? The word saltatory comes from the Greek word, it's actually Latin. The Latin word saltere, which means to jump. Because the action potential appears to jump from one node of Ranvier to the next. Where do you think the action potential travels faster? In an unmyelinated or in a myelinated like this? In a myelinated. Because it skips areas. It's jumping. It's literally jumping over areas of the nerve fiber. So in an unmyelinated nerve fiber, every single part of the nerve fiber has to change this. Sodiums have to flow in and potassiums have to go out. In a myelinated, it leaps or jumps from one node of Ranvier to the next. So the conduction velocity how fast this action potential travels is faster in a myelinated than in an unmyelinated. Let's go back to page 50. So back on page 50, what did I write on page 50 about myelinated? The depolarized node of Ranvier triggers the increase in permeability and thus depolarization in the adjacent node of Ranvier. That's called saltatory conduction. Now, conduction velocity in nerve fibers is affected actually by two things. Two factors affect how fast the action potential travels. The diameter of the nerve fiber and whether it's myelinated or not. We've already mentioned that myelinated nerve fibers conduct faster than unmyelinated. But the first factor is the size of the nerve fiber. The bigger it is in diameter, the faster the conduction velocity. That's because if it's larger in diameter, there are more sodium channels. Because it's bigger. There's more sodium channels. So those are the two factors. The larger the diameter, the faster the conduction velocity. Whether it's myelinated, it's faster than an unmyelinated. We can see these two extremes in a picture on the next page. On page 51 are pictures of two nerve fibers. These are the extreme versions of this. At the top is a thin, skinny, unmyelinated nerve fiber. Right below it, a big, thick, myelinated nerve fiber. This, and we have every combination in between. We could have a thin, skinny, myelinated, and we could have a big, thick, unmyelinated. All right? But these are the two extremes. Here is where the action potential travels slowest. Here's where it travels the fastest. Let me just see if there's anybody outside right now. Yeah, there's nobody here right now. This is what I like to do is I usually like to see if there's a student outside, and I invite them in, and I ask them the following question. These are you students who haven't had physiology. And I ask them, first of all, are you aware that the nervous system sends electrical signals? Everybody says yes. Everybody knows the nervous system sends electrical signals. So I ask them, okay, do you think that the electrical signals in the nervous system travel at the same speed that electricity travels in a wire?
No.
They always say yes, because most people think that. Most people think that these nerve impulses, these action potentials, are traveling at the exact same speed that electricity moves in a wire. It's not even close. First of all, you already know that they don't all send action potentials at the same speed. That's what we've implied right here. So, right below, the conduction velocity, how fast electricity travels in a wire, is 186,000 miles a second. That's called the speed of light, or 300 million meters per second. 3 times 10 to the 8th meters per second, 3 times 10 to the 10th centimeters per second. That's how fast electricity is traveling in a wire. The same speed that light travels at. Now, how fast do the action potentials travel in a nerve fiber? In the biggest, thickest, most myelinated nerve fibers, about 100 meters per second, which is about 300 feet per second. Now, if it's unmyelinated, it travels slower. In some thin, skinny, unmyelinated, it travels about a half a meter per second. In the thick myelinated, up to about 100 meters per second. How does that compare with how fast electricity is traveling in a wire? Is this even close? Not even close. So there are electrical currents moving in your nervous system, but it's nothing like electricity moving in a wire. Why not? There are a number of reasons.
Chemicals?
Huh?
Is it chemical exchange?
There's a number of reasons. First of all, what's moving in a wire?
Electrons.
Electrons. What's actually moving here are sodium ions. Now, for a lot of us, we're thinking sodium ion, electron, I think it's the same thing. It's nothing the same! It's not even close! Do electrons weigh anything for all intents and purposes?
No.
They weigh nothing. A sodium ion is an electrically charged sodium atom with 11 protons, 12 neutrons, and a bunch of electrons around it. To compare a sodium atom with an electron would be to take the sun and compare it with a pea. Does that sound about right?
Yeah.
The sun compared to a pea is like an atom, a sodium atom compared to an electron. So what's moving is something totally different. Secondly, the medium in which it's traveling. The electrons are being transferred from one copper atom to the next. What's moving in a nerve fiber is sodium ions are moving through living cytoplasm. So this is very different. We have electrical charges moving, but it's a different kind of electrical charge, and it's moving through a totally different medium. Living cytoplasm versus copper wire. All right. Now, so we do definitely understand that while our nervous system sends these electrical signals called action potentials, they're not moving anywhere near the same speed as electricity or wire. Let's talk about multiple sclerosis. Has anybody ever heard of that? Commonly called MS. Now, MS is an autoimmune disease. In MS, an autoimmune disease, your white blood cells, your antibodies, your immune system attacks and destroys the myelinating cells, the oligodendrocytes and Schwann cells. That's what it attacks. So, in fact, an MS is called a demyelinating disease. Here's a picture I've already drawn, and I'll just kind of walk you through this. This is a myelinated neuron. It has a fast conduction velocity, right? The first thing that happens in MS is the immune system destroys these myelinating cells. If the myelinating cells are destroyed, that makes this nerve fiber unmyelinated. What does that do to the speed at which the action potential is now moving through the nerve? It slows down. The first symptoms of MS is a slowing of the conduction velocity of impulses in the nervous system. The person's finding they can't run anymore. They can only walk quickly. Then they can't even walk quickly. They start to walk more slowly. Everything is moving. These impulses are moving at a slower speed through their nervous system. But then, it causes a conduction velocity slow. And then it gets worse. You'd say, what happens next? What happens after the immune system destroys the myelinating cells is scar tissue forms around the unmyelinated nerve fiber. You'd say, what? Scar tissue forms. Now, what is scar tissue? You learn scar tissue in anatomy, right? It's irregularly arranged dense fibrous connective tissue. Dense fibrous connective tissue is fibroblast cells that manufacture and release collagen. That's scar tissue. It's important to know scar tissue because scar tissue forms anytime there's injury to the body. Anytime you injure any part of your body, scar tissue forms. So basically the nerve fiber has been injured and scar tissue forms around the entire surface. Now, whenever scar tissue does form, whenever scar tissue forms in the body, there are two words that are used: fibrosis and sclerosis. They call it fibrosis because it involves fibroblasts. Those are the principal cells in scar tissue, irregularly arranged dense fibrous connective tissue. And scar tissue is hard. It's tough. And that's why they call it sclerosis, which means hard or tough. So an example of what I'm saying is when scar tissue forms in the wall of an artery. What do they call that if it forms in the wall of an artery? Arterial sclerosis, which is commonly translated as hardening of the artery. And that happens with injury to your arteries, arteriosclerosis. In this case, scar tissue or sclerosis is occurring around all the nerve fibers. That's why this disease is called multiple sclerosis. It's sclerosing or forming scar tissue everywhere in the nervous system. Now, what happens as the scar tissue forms is the sodiums cannot enter at all. If the sodiums can't enter at all, now this nerve fiber isn't conducting an action potential at all. So what we see is a progression. First, we have normal myelinated nerve fibers sending impulses at a fast speed. The myelin cells are destroyed by the immune system, so the conduction velocity gets progressively slower. And then as the scar tissue starts to form, and now sodiums cannot enter the nerve fiber at all, conduction velocity ceases. It stops. Now they're paralyzed. Now they can't walk at all. So they start out where they can't run, and they're walking slowly. Then they're in a wheelchair, and they can't walk at all. Eventually, as the nervous system can no longer send action potentials, not only is there paralysis of muscles that move your arms and legs, so they can't walk, but the most important skeletal muscle controlled by the nervous system is the diaphragm muscle. They can't breathe out. Either the white blood cells are not able to recognize the myelinating cells as being the person's own, or the myelinating cells lack those recognition sites on the outer surface. Something's gone wrong. All right, so that's MS. So what did I say about MS? It involves degeneration of the oligodendroglial cells and Schwann cells and replacement by scar tissue, called sclerosis. Thus the name multiple sclerosis. It's associated with paralysis, tremors, disturbances in speech, depending upon the location of the lesions. The word lesions means damage. And in different people, the damage begins in different parts of their nervous system. It may begin in the central nervous system, it may begin in the peripheral nervous system. The etiology, these are all good clinical terms. Lesion means injury, you should know that. Etiology means cause of a disease. These are good clinical terms. It's an autoimmune disease. There's an antibody cross-reaction with proteins of the body. Something that I'm going to tell you more about at another time is that all autoimmune diseases are triggered or brought on by an infection. So if you've had micro, you may have learned that what brings on rheumatic heart disease is beta hemolytic streptococcus viridans infection. All right? So when the person, basically what's happening is the person's immune system attacks the bacteria, which is fine. It then starts to attack the heart, which is not fine. MS is triggered by a viral infection. But when people get a particular viral infection, their immune system attacks the virus, and then it starts attacking the myelinating cells. So there's some sort of cross-reaction. The immune system can't tell the difference between the bad guy and their own body. On the next page, 52, there are many, many, many autoimmune diseases. Hundreds of them. Hundreds. Literally hundreds and hundreds. They include rheumatoid arthritis is autoimmune, attacking where the immune system attacks the joints of the body. Rheumatic heart disease, where the immune system attacks the valves of the heart. Lupus erythematosus, or lupus, where the immune system attacks the skin and other parts of the body. Glomerulonephritis, where the immune system attacks the kidneys. And I added a fifth, juvenile onset diabetes, known as type 1 diabetes, or juvenile onset. When somebody who's a kid develops diabetes, this is not because, they've got, they're overweight and they've been eating too much donuts their whole life. This is their immune system has destroyed the beta cells, the beta cells in the pancreatic islets. So their beta cells have been destroyed by the immune system, so they have to inject insulin for the rest of their life, or get an insulin pump. Now, how do you treat an autoimmune disease? One of the approaches, since it's the immune system attacking the person's own body, is to give drugs called immunosuppressants. We've talked about this before. Suppressants are drugs that inhibit the immune system. The most commonly used drugs for immunosuppression are corticosteroids like prednisone. So when people have autoimmune diseases, they may be given corticosteroids like prednisone. All right. We've been talking about the generation and conduction of action potentials.